In this example, we're going to take a look at a bar in tension, determine the displacement fields, and then see if it's an admissible displacement field, and then do a couple other little things with that information. Alright, so first of all, we're going to put our coordinate system at the center of the bar, and we're going to pull on both sides. It's going to be in equilibrium with some level of force. The material is going to have a Poisson's ratio of nu and an engineering axial strain in the bar of A, and we're going to make sure that A is much less than 1. So this will be typical of elastic engineering strains, maybe 1 or 2,000 microstrain for a piece of steel or something like that. Alright, so first of all, we want to figure out what the displacement fields are. With respect to our coordinate system, that coordinate system kind of represents a plane of symmetry. So at that spot, right at the very origin, we can say that if the loads are equally applied, there is no displacement at the very middle of that system. The displacement will increase linearly as we move away from that origin of that coordinate system. So we move in the positive x1 or the axial direction, we'll have positive values of displacement. As we move downward in the negative x1 direction, we'll have negative values of displacement. The further we are from the origin, the more displacement we have, because there's more material that stretches on either side. So with this, we can write down our displacement field in the one direction as equal to A times x1. We can also write down our displacement fields in the 2 and the 3 directions. They'll actually be the same, and due to Poisson's ratio, we can say the displacement in the 2 and in the 3 directions, if we have a positive value for A, we'll have a negative value for these other displacements. Minus nu A x2 and minus nu A x3 for the displacement field U2 and U3. So the question we want to answer is this admissible? Now the way to determine if it's admissible is to check our Jacobian. We're having the restriction that our Jacobian has to be positive, can't ever be 0, and the way our system is set up, it can't ever be negative. And the way to check that is by checking the determinant of a matrix formed. Oops, these are partial derivatives. Partial derivative of xi I with respect to xj, where xi represents the new position in the deformed coordinate system of the deformed body, and x is the coordinate in the original body. We will have met our continuity restrictions, so we're not breaking this. This is just a pure stretching or compressing of the material if A is positive or negative. Now, of course, if we remember, the final position of the body is equal to the initial position of the body plus the displacement. So when we evaluate this, we're going to evaluate this in the form of the determinant of partial derivative of xi with respect to xj, which is Kronecker delta ij, and then the partial derivative of ui with respect to xj, which we can use as the common notation ui comma j. So we need to find some partial derivatives. We'll go ahead and list them all right here. Partial derivative u1 with respect to x1 is a, u1 with respect to x2 is 0, u1 with respect to x3 is 0, u2 with respect to x1 is 0, u2 with respect to x2 is equal to minus nu a, u2 with respect to x3 is equal to 0, and then for the last row, u3 with respect to x1 is equal to 0, u3 with respect to x2 is 0, and u3 with respect to x3 is equal to minus nu times a. Now, one thing I want to point out about this coordinate system is that we're not free to place this coordinate system anywhere and use these displacement fields. Suppose we decided to put our coordinate system on the outside surface of our round bar. Well, then we'd have to adjust our displacement fields accordingly and use different equations. So this displacement field is very much tied to the placement of our coordinate system. Alright, now that we have these partial derivatives, let's go through and list the matrix for this expression right here. And again, remember, it's got the Kronecker delta in it. Let me make, maybe I can get it in here. So we're going to do the determinant of a matrix formed by Kronecker delta 1, 1, which is 1, plus the partial derivative u1 with x1, which is a. Kronecker delta 1, 2 is 0, and the partial derivative is 0. Kronecker delta 1, 3 is 0, and partial derivative is 0. Partial derivative, well, Kronecker delta 2, 1 is 0. Partial derivative is 0. Partial derivative of u2 with respect to x2 is minus nu a, but since we have the Kronecker delta 2, 2, we have to put a 1 right here. And that'll be a minus nu a. And then we have zeros here and here. I'll let you go through that and verify that. And then the last term we have is another 1 minus nu a term. So what we want to do is we want to find the determinant of this matrix. Let's make a little bit of room. As far as determinants goes, this is a pretty easy calculation. We're just going to multiply these three diagonal terms. If you haven't done determinants of 3 by 3 matrices in a while, it wouldn't be a bad idea to start reviewing that now, as we will get a little bit more involved in matrices later in the semester. So we have 1 plus a, and then we have 1 minus nu a, and we have two of those, so we're going to square that. And then the question is, is this admissible? Is j going to be greater than 0 in this case? Well, if we look at the second term that's squared, obviously whether a is positive or negative, since we have 1 minus whatever that is, and we square that value, then we are going to get a positive value. The first term we have 1 plus a, but remember we said that a was much less than 1. So whether that a is positive or negative, the first term is going to be positive for us. Okay, so the answer is yes, and this is an admissible field under the conditions that we have set for it. Alright, now let's compute the strain tensor for this deformation field that we just talked about. So it is, in general terms, we can say that epsilon ij is equal to 1/2 partial of ui with respect to xj plus the partial of uj with respect to xi plus some terms here that look like partial of ul with respect to xi, partial of ul with respect to xj. Now, for this particular coordinate system, now we have to remember that components of a strain tensor are tied to a coordinate system. The strain tensor itself is a coordinate system free entity, but when we talk about components, then we have to be talking about a specific coordinate system. So in this specific coordinate system, we noticed on the previous page that a lot of the partial derivatives were 0. In fact, in any case where I and j are not equal to each other, the partial derivative is 0. So we're only going to have non-zero terms that look like epsilon 1, 1, 2, 2, and 3, 3. The off-diagonal terms are going to be equal to 0. let's go ahead and write down a couple of these terms just to get a little more practice with our index notation. For example, epsilon 1, 1 will be equal to the partial derivative of u1 with respect to x1 plus partial derivative of u1 with respect to x1 plus the summation u1 with respect to x1, u1 with respect to x1 plus u2 with respect to x1, u2 with respect to x1, and u3 with respect to x1, and u3 with respect to x1. Now, in this particular case, this term is 0, this term is 0. We have a half out in front. We said that this was equal to a. That term is equal to a squared. If we wanted to, since a is much less than 1, if we square it, a squared is negligible with regard to the term a. Let's go ahead and drag it with us for now, though. We can say that epsilon 1, 1 is equal to a plus 1/2 a squared. Okay, now epsilon 2, 2 will be very similar. It's going to be 1/2. Now this is going to be the partial derivative of u2 with respect to x2. So that was equal to minus nu a. And we have another one just like it. And then we have u1 with respect to x1, u1 with respect to x2, u1 with respect to x2, which that term is 0. And then we have a u2 with respect to x2 times a u2 with respect to x2. Now that is going to be a plus u squared a squared, which is going to give us a minus nu a plus 1/2 nu squared a squared. And if we do the math, we will see that because of the nature of the displacement field, we'll get the exact same value for epsilon 3, 3. As I mentioned, due to the nature of this displacement field, these off-diagonal terms are all going to be equal to 0. So if we want, we can make our components of our stress tensor in this coordinate system. We can write this in matrix form. A plus 1/2 a squared, 0, 0, 0, minus nu a plus 1/2 nu squared a squared, 0, 0, 0, minus nu a plus 1/2 nu squared a squared. Alright, well, let's talk about what's going on in the material as far as the deformation goes. And so we have our bar, and in our bar, I'm going to imagine that we consider this about our coordinate system if that makes it more convenient. We can imagine that there's a sphere in the material, and in that sphere we have dimensions of the diameters, or the radius if you want, of 1 millimeter. And this is what the bar looks like before it's deformed. So if we think of our bar again, this sphere is sitting right at the center of our origin, something like that. Well, we're pulling on this, and I'm going to exaggerate this. This bar stretches out. This sphere is going to distort. It's going to get longer in the axial direction, and it's going to get shorter in its axes in the transverse directions. Again, I'm really exaggerating this. If A is small, it won't make a big difference. But what happens is that the sphere distorts into an ellipse. Let's see if I can do this. So if we look at the 2D plane, maybe it takes a shape something like that. And since this is in 3D, I guess we should really call that an ellipsoid. Okay, so it's the picture after deformation here. And it really makes sense in this particular case, but what we'll find out is that for any continuous body that undergoes a deformation, we can imagine there being a strain ellipsoid that came from a sphere in its original configuration. We'll find later that the major and minor axes of the ellipsoid correspond to directions of principal strains or eigenvectors and eigenvalues of the strain tensor. We'll get into all that later, but when we get to that point, we'll kind of bring this idea of the strain ellipsoid back up. Well, we have enough information now that we can actually compute the major and minor diameters of the ellipsoid. And we can do this based on our definition of our magnification ratio. If we recall, that's d script s by ds. Okay, and so in this case, this would be our d script s in that direction. We have another d script s in the horizontal direction. So d script s by ds is equal to square root of 1 plus 2 times the magnification factor for that particular line. And we can find the value of the magnification factor by knowing the components of our strain tensor, epsilon ij, and the unit directions. If we write it in this form, ni in j. So let's take a look at the vertical diameter, or the major axis. Now we have to remember that these two refer to the directions in the original coordinate system. So in this original coordinate system, this direction is the x direction, this would be the n direction, and that direction would have components 1, 0, 0 for its unit vector. Has to be a unit vector. So we would take this epsilon ij and multiply it out by ni in j in order to find that magnification factor. Alright, so let's see. We did the matrix form previously. If we multiply this term out this time, we would have 9 terms in this expression. We'd have epsilon 1, 1, n1, n1. We'd have an epsilon 1, 2, n1, n2. Let's go ahead and do the double summation. We'll go ahead and write out all 9 terms. We haven't done that in a little while. If you notice the way I write it, I tend to write it in terms of a matrix format. Of course, the strain tensor is symmetric. And I'm writing it initially as a non-symmetric term, and then we go back and account for the symmetry later. Alright. Now with n1 being the only non-zero component of that unit vector, we end up being able to quickly reduce this down to just epsilon 1 times 1 times 1. And so this magnification factor then would be a plus 1/2 a squared. Now we've written previously that this magnification ratio is related to the magnification factor through this relation. d script s by ds is equal to square root of 1 plus 2 mf. So for the major axis, magnification ratio is going to be equal to square root of 1 plus 2a plus a squared. Now we do something very similar for the minor axis. The magnification ratio for the minor axis will be given by the same expression, but this time we're going to use the 0, 1, 0 unit vector. And then in that case, the only term that will be left will be the epsilon 2, 2 into n2 term, where n2 is both equal to 1. So the magnification factor is going to be equal to minus nu a plus 1/2 nu squared a squared, giving a magnification ratio for the minor axis being equal to 1 plus minus 2 nu a. Let's go ahead and get rid of that plus sign. Plus nu squared a squared. And since the displacement field in the 3 direction is the same, then this will work for either minor axis. They're equal. Alright, well, let's put some numbers in here and let's see what this means. So suppose A is equal to 1,000 microstrain. Remember, 1,000 means times 10 to the minus 6. And Poisson's ratio for a typical steel, say, is about 0.3. Well, we can put these in here, and for the major axis, if our original dimension is 1 millimeter, we can go through and find our new d script s would be equal to 1.001 millimeters. And then the minor d script s we can find to be 0.9997 millimeters. Okay, and so that's how you would use these magnification ratios and the magnification factor and the strain tensor to find out what's going on in that material. Now you know how long that new line segment is after that deformation. We understand when we pull a bar in tension that the Poisson contraction causes it to get skinnier in the transverse directions. And here we have, for a 1 millimeter length, exactly what that would be under these conditions. Alright, so again, the sphere in the original configuration turns into some sort of ellipsoid. We're going to relate that to principal strains and eigenvalues and eigenvectors. And this is a term, I'll kind of highlight this. Our book gets into this just a little bit. This is called the strain ellipsoid, so that's kind of an interesting concept.